Bismillah ar-Rahman ar-Rahim. This is Steel Structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University on April 5th, 2020. Today, inshallah, we're going to start with chapter 5, beams. And what is the definition of beams? Beams are structural members that support transverse or vertical loads, and they are mainly used to resist bending or flexion. And the most common used cross-sectional shapes for beams are wide flange, and we do have S shape or M shapes, and we might have channel shapes or American standard channels or shapes. Sometimes they are used for built-up sections with plates and etc. Standard hot-rolled sections, they are the most common used shapes for beams because they are the most efficient. So when we tell they are the most efficient, what does it mean? So let's talk about the wide flange. Wide flange, because the moment of inertia is going to be large for such shapes, and from the basic flexure equation, the bending stress is equal the moment times y dividing by I, or this one is equal m dividing by elastic section modulus. So m here is the moment, or let's say this is the maximum moment. And this one here, this is the distance between the neutral axis to the extremist fiber, okay, whereas the yielding starts. And I is the moment of inertia. So if we have a cross section with a large value for I, this will be smaller, means the moment of inertia is inversely directed to the stress, okay? And this is a bending stress. There is a difference between a bending stress and an axial stress. For the axial stress is equal P over A. So P is the force and A is the cross-sectional area. This is axial and this is bending stress. So as I mentioned, hot roll, they are commonly used for the beams. Okay? Okay guys, so right now if we have a beam, how to measure the strength capacity of this beam? In chapter 4 and for the column, we used to use the strength, which is the force, kips. But in this chapter for the beams, as the beam, they are mainly used to resist the bending moment. So we will use M here, MU, and MU here is the maximum moment caused by a controlling load combination from ASCE 7. If you remember, we had in chapter 2 7 load cases, and you have to pick the largest or numerically largest value. So this moment is going to be the maximum moment under which load case control. Okay. So this MU require moment strength, which is in a different words the maximum moment under the load. Okay, yani if you do have a beam, let's say simply supported beam, and let's say it's loaded with a distributed load or uniform distributed load downward here. So the maximum moment is going to be at the mid, and this one is equal WL square over 8. This is just an example, guys. And this is the maximum moment. That's what we need to compare with the capacity of the cross section, okay? So, and phi B here, phi and B for bending is the resistance factor for bending, and bending or flexure, they are same, just different terminology. So this one is going to be 0.9, okay, for flexure. And Mn here is the nominal moment strength, okay? This is nominal moment strength. As we had nominal strength in chapter 4 for columns, here we're gonna have nominal moment strength. Okay. So this one is, okay, here is nominal moment strength. Okay, so here guys, this side of the equation, which is the right side, this is what we call it design moment strength. Okay, this is what we call it design moment strength, okay? Okay. And this equation, guys, here, it's for LRFT method. Okay, so what about AST method? How we can calculate the allowable strength design? Let's move down and see how to do that. I'm gonna go back and comment in these two figures here, okay? Okay. So for the allowable strength design, which is this one, guys, ASD method, we're gonna have MA here, which is the required moment, is the same, is gonna be the maximum moment corresponding to the controlling load combination from ASCE. But here, if you remember for ASD method, we just gonna have the surface loads combined together, and there are some factors, they are not the load factors, okay? So one of the, I think case number 1 was D, case number 2 D plus L, and so on, okay? We do have several cases. So here M is going to be the maximum moment under the control or controlling load case. My 2 is going to be the control load. So that will be the maximum moment, okay? And this is the safety factor for bending, which is equal 1.67, okay? So here, MA is supposed to be less than or equal nominal moment, okay, dividing by the safety factor, and 1 dividing 1.67, which is the safety factor, is equal 0.6, and we can write it in this way, okay? So right now, I showed you the equation for LRFT method and this one for the ASD method, okay? In this case, guys, just a quick note here. If we do have this one here, okay? MA is less than or equal 0.6 MN, which is the nominal strength. If we divide both by elastic section modulus, which is S, and here dividing by S, and S, guys, is the elastic section modulus, okay, here, guys, it's equal moment of inertia over Y, okay, and that's what we call it elastic section modulus. Okay, and we do have a plastic section modulus, but this is not our interest here. Okay, in this case, we're gonna have the bending here, stress, and this one is gonna be like this. So bending stress is supposed to be less than the bending stress or the allowable bending stress here. So here is the maximum bending stress. It's supposed to be less than the allowable bending stress, okay? This one is going to be same to this, but they are dividing by S, so we turn it to stress. As promised, these two figures, this or these are wide flange cross sections. But this one is a hot rolled cross section, which is the standard shape. So you see there is no welding, and this is H, this is the web thickness, it's okay, same here. But this one, guys, is a built up section. So these are blades, look at this, okay? These are blades here, welded here. If you look, this is the welding area, together to form what we call it plate girder, okay? And this is a built up section, okay? This is a built up section, and beams might be either a standard or hot rolled sections or a built up section, and this is what we call it plate girders. And let's move on. As I promised, guys, this is a wide flange shape, and this is a wide flange shape. But what is the difference? Here, this is a hot roll cross section, which is a standard cross section, and you see this is one piece, and there is no any welding or bolting. And this one, it's the height is H, and this is the web thickness. And similarly here, but this one is like a plate. Okay, we do have plates here and there, and they are welded together, and this is a welding area, okay? Welded together to form what we call it a plate girder, okay? This is a plate girder. Okay. This is a plate girder, and that's what we call it again. It's a built up section, okay? It's a built up section or shape. So, and once again, why we need to do a built up section? Because sometimes the available standard shapes will not be good enough to carry the subjected loads. So the first step, we need to determine the nominal moment strength, which is Mn here. Okay, and let's first check the behavior of the beams under the loading, let's say from very small loads to the point of collapse or forming a plastic hinge. So here, let's consider this beam here, okay? If we do have this beam, this is a simply supported beam, okay? Simply supported because there is a pin here and another or a roller here at the other end. So, and loaded with a distributed load, a uniform distributed load, and we do have two single constellated loads. So here, if we take an imaginary section, we can get the shear and the moment, okay? But actually, we need to find the reactions before doing anything like this. So if we take the cross section here, guys, so this is the cross section. This is the profile here, and this is the cross section, okay? So if we take the cross section here, so this is the x-axis, and here is the C or the Y, which when I told you M times, let's say here C dividing by I, this is the stress. So yeah, this is the distance from the neutral axis or here, because the neutral axis here is going to be similar to the here, because this is a symmetrical shape. So the neutral axis will passing through XX here. So this is going to be from the neutral axis to the maximum or the extremist fiber, okay? So right now, under a small load, and for the linear elastic material and under a small load, there will be a small deformation, and the stress here here, guys. So here, so this is going to be the stress. Okay, actually this is a tension stress, this is a compression stress. Okay, so here the bending stress distribution, which is here, it's assumed to be uniform across the width of the beam. Okay, so this will be uniform. And here we do have at, let's say, point Y from the neutral axis, we have the stress is equal F sub B. Okay, and if we keep increasing the load, we will get the point where is the yield stress starts, and will keep going until we have a plastic hinge. Let's move on here. And here, guys, as I just mentioned to you, F sub B is all the time equal M times Y times I here. Okay, so Y is the perpendicular distance between the neutral axis to this point, which is Y. And because I just mentioned this is a symmetrical shape, so the centroid or the neutral axis is all the time conform or coincides with the centroidal area here. Okay, أنه متشابه. Now, if we need to calculate the stress at any point, we're going to use the basic fluxure equation, and the moment will be max, or the stress will be maximum. Let's use the same here. So F max here, which is the stress, is going to be where Y is equal C. So here it will be there is a moment, and will be here more, and here will be, and the maximum value is going to be here. Okay, maximum value, and you look here, the maximum value is going to be here, it's going to be greater than here or wherever, and here will be same. Okay, if we have a symmetrical shape. So and it's okay, we know how to do that. And here, guys, if you keep increasing the loads, you will get a point where is the F, or the stress, will equal, just a minute. The F, which is the stress, will, or max here, will get equal Fy, and here is the yield stress. Okay, this is the yield stress. So if we design the material, or for, let's say, small loads, the material should be within its linear elastic range. So My here, it's going to be, because it's going to be, should not exceed this. So the maximum moment, guys, because Fy here is equal My here, the yield. M sub Y, okay? This is M sub Y. Let's make it clear. This is M sub Y dividing by elastic suction modulus about x-axis, because here is the bending axis. And this is the yield stress, okay? And this is the yield moment. لما أحكي yield, that means the moment where is the section starts to yield, okay? So let's take this one here and see this example. So guys, this is going to be a good example to show you how the load will be increased and how will affect the cross section. So if we have a simply supported beam again, but here it's loaded with a concentrated load at the mid. So this is the moment, if you assume this is going to be here like this, okay? Because the shear is going to be like this, up, and then we'll stick like this, and then we'll continue like this, and then like this. This is going to be the shear. This should be once again here, guys. So the shear, let me pick a different color, will be like this. We're gonna, if this is the neutral axis, we're gonna go up, continue, go down, continue. This is the shear. Okay, if this is positive, this is negative, and if we need to draw the bending moment, pick a different color. So here, bending moment is gonna be, we're gonna start with 0 here, okay, and we're gonna go up here and then go down. Actually, it's supposed to be here. Okay, so this is the maximum moment where we do have a 0 shear here. Okay, so right now, after, let's say if and let's call this P or P. If P is very small, we're gonna have a distributed load here, but it's gonna be very small, so the stress is still less than F yield. And just a minute here, so this is a tension and this is a compression here. So, but the maximum value here is still less than Fy, which is the yield stress here. طبعا هون we still have a very small load. If we keep increasing the load, we are at some point we will get where is the maximum stress will be equal to the yield stress, as I just mentioned to you. Okay, and let's move and see what if we increase the load. If we do increase the load or keep increasing the load here, at some point, guys, we're gonna start having a plastic zone. So here, guys, if you see here, so just this fiber is yielded, but still, and this one from the top and bottom, but still there is an area here, it's not yielded yet. See? So just this one yielded, but this one is not yet. So here, guys, the yielding will continue here and this one. So we're gonna call this, or this area is a plastic area. Okay, but we still have elastic area. And if we keep doing this, and this one is equal Fy, if we keep increasing the load, so the section will be fully plastic section, and this is the stress distribution here, and this one is tension, this is compression. So here we tell that we have a plastic hinge, okay? And once actually, guys, the yield or the extremist fiber starts to yielding, the stress is not going to be linear anymore. This is okay, linear here, still linear, but here is not going to be linear, okay? And as you see here, the yielding will progress towards the neutral axis, because this is the neutral axis. So it will start from the extremist fiber to the yielded or neutral axis. Okay. Okay. Once we got to this point, so that means that the cross section is entirely yielded and plastic. If you increase any load, you will get a collapse. Okay. So this section will fail and راح ينهار يعني at this moment مش راح يقدر يحمل أي load إضافي. So at this point, if you notice here, guys, we start having, okay, this is the yield stress here, this corresponding to this. And once we have this case, the plastic hinge form is formed, okay? So that's what we call it, the plastic hinge. So just imagine that we do have something like this. So this is the simply supported beam. So at a plastic hinge formed, that means under the load here, we have such thing like this. So here, imagine we do have a hinge. Okay. Okay, guys, we need to calculate the plastic moment capacity. And the plastic moment capacity is how much moment we need to create this plastic hinge for a simply supported beam in this case, okay? So this is the cross section, guys. Okay, this is the cross section here. And this is the neutral axis, or what we call it a plastic neutral axis. But actually, for let's say symmetrical shapes, elastic and plastic neutral axes are same. So we do have a elastic neutral axis, which is the one that we use to find it in static, structure 1, structure 2. But the plastic is different, okay? So the plastic neutral axis divided the cross-sectional area into two equal areas. Yani in this section, this area here equal to this area here. And it might be not in the middle, but this one, because it's a symmetrical one, okay? So that is the definition of the plastic neutral axis, which is the one that divided the cross-sectional area into two equal area. So if this is area, we call it 1. So this one is going to be area equal 2. In this case, area 1 and 2 equal each other. And this one is going to be the compression area. This one is going to be the tension area. So in this case, okay, this is the, just to clean it up. So this is the fully yielded cross section. And here we do have a compression. And here we do have a tension, okay? So in this case, guys, so this is the equivalent force here. And T here is the tension, because in the beam, for sure, this is going to be tension, okay? And the up is going to be compression, okay? So here, guys, we do have, this is a tension force, is the area under tension times the yielded stress, because this much is yielded stress, okay? And this one, guys, here is equal to the compression force, which is area under compression times Fy, okay? And this is the distance A between the center of these two plugs, okay? The distance between the compression and tension forces, okay? So the plastic moment is gonna be here, guys, because as I just mentioned to you, for the neutral or plastic neutral axis, T is equal AC here, okay? So here, for equilibrium, so C is equal T, which is the force in compression, is equal force in tension, and this one is equal to this one for equilibrium of the forces. And C is AC times Fy, which is equal to AT times Fy. Okay, here, guys, Fy is equal to Fy. That's what I just told you, that AC is equal AT, and this is for this case we can tell, okay, this is the plastic neutral axis. Okay, how to calculate the moment here? So I'm a plastic here, I'm sub P, and P here stands for plastic, is equal here. If we take, this is a couple moment, yani we have two forces, same in magnitude, but different in direction, okay? And they have a perpendicular distance. So if we take a moment here, this one is going to be, let's say, Fy times AC. Oh, sorry, AT here. Let's keep it AT because I'm taking it here. If you take it here, is okay. So this is the force magnitude times the distance between this point and this point, which is A. Okay, and this one here, it's going to be same if we do it Fy times AC compression force times A. Okay, they're going to be same. So if we do that here, guys, we're going to have Fy, and as I told you, AT and AC is the half of area, okay, because this is the neutral axis. So this one is equal A dividing by 2 times A. Small here is the distance here. And نشوف هون AT و AC they are equal A. And as I told you, this plastic neutral axis dividing this area into 2 equal areas. So in this way, guys, we're gonna call this Z. So this is gonna be FYZ. So briefly here, guys, M plastic or plastic moment is equal Fy, which is the yield stress, times Z, and Z here times Z. And Z here is the plastic section modulus. Plastic section modulus. Okay, and if you remember S, elastic section modulus, this is plastic section modulus. Okay, S was equal I over, let's say, C or Y, the distance between the neutral axis to the, in the case of the elastic section modulus, or let's say in case of elastic section. Okay, but in plastic we have Z. Okay, but here is different how to calculate this. So, okay, guys, let's solve this example and see how we're going to calculate elastic section modulus S, yield moment, and plastic moment. So, in this example, the problem statement says for the built-up shape shown in this figure, which is this one, guys, okay? First, we need to determine the elastic section modulus, which is S, which is I over Y or C, okay? This is S, elastic section modulus. It's elastic section modulus. And the yield moment. And we will know how to calculate the yield moment, okay? And B, we need to calculate the plastic section modulus, which is Z, and the plastic moment, which is M sub P. Bending is about the x-axis, and the steel is A572 grade 50, and this is commonly used in the steel bridge. So this is the x-axis. So here we do have all the information we need to do the calcs, okay? Okay, so this is the beam that we do have. So these are the dimensions we need, the thickness for the upper and lower flange here. And we do have the width is 8. And we do have the depth from the bottom of the upper flange to the top of the bottom flange is 1 feet. So right now we need to calculate I, and if you see, guys, here, first of all we need to start calculating the neutral axis, and the neutral axis is going to be Y times A, or summation of Y times A dividing by summation of area. But here we do have a symmetrical shape, so we don't need to do this. And the neutral axis is going to be at the mid here. So this is the neutral axis. So we just need to start calculating the I here. So I here, guys, if we move down, we need just, before doing that, we need first to calculate moment of inertia here. And the moment of inertia for the bottom flange, and we need to calculate the moment of inertia for the web. For these two, the upper and lower flanges, we will calculate the moment of inertia about its neutral axis and then move it here using parallel axis theorem, okay? And I'll show you how to do that in a table form here. So right now, let's move down. So in this table, guys, pick a different color. Okay, so for, let's say, for the bottom flange here, so let's call this bottom flange. Okay, for the bottom flange, because the bottom flange is like this, we do have the width is 8 and the thickness here is 1 inch. So the moment of inertia for this is going to be P times HQ dividing by 12. And P here is 8 times 1 cube, which is the thickness, or H, dividing by 12. And this is going to be equal to this value. And similarly, for the upper flange or top flange, because they are similar to each other, we will get the same value. For the width we do have, it's like this. Let me do it here. This is to the exaggerated scale. So the width is okay, this is 1/2 the thickness, and the top here, which is the H, and this equal 1 foot, which is a 12 inch. 1 foot is equal 12 inch. So here the moment of inertia about its centroid, which is going to be equal to 1/2, which is the B, times 12 to, or 12 cube, dividing by 12, and this one is going to be equal 72. Okay. Okay, right now the parallel axis theorem is equal. I is equal, let's say I hat plus A times D squared. I, the one that we did calculate here, for a rectangular PH cube dividing by 12. Area, it's easy. For the two flanges, area is 1 times 8. Here 8 inch square, 8 inch square. And for the width, we don't need to do that. Why? Because here are the two flanges. So here is the neutral axis. For the width, we don't need, because the moment here of inertia is about its neutral axis, which is coincides with the neutral axis for the whole shape. So we don't need to do parallel axis theorem. Look at this one, 0, 0 here. But for the two flanges, the moment of inertia we just calculated, which is this one and this one here for the bottom and upper flanges, is going to be around the neutral axis here. So this one here, this distance is equal D, which is same to this, which is the distance between the neutral axis of the area or centroid of the area to the neutral axis for the whole shape. So this is D. Okay, so here guys, A, we just calculate how we got 6.5. 6.5, let me pick a different color. So here we do have this here, from this point to this point, 1 foot, which is 12 inch. Okay, but the neutral axis, or the D, is from here, which is half of the thickness plus this, and this one here till this point is going to be 12 over 2, which is 6. So 6 inch plus the half of the thickness here and here, it's going to be 1/2, and the thickness is 1. It's going to be 6 plus 1/2, 6.5. Okay, and same upper, top, or lower flanges, or they are equal. So right now just do this. This one plus this times this square is going to be get this value, and that is same for the bottom and upper flange. And this one we don't need to do anything with this one. So the moment of inertia for the whole shape is 749.4 inch to power 4. Okay, this is inch to power 4. So the elastic section modulus S is I dividing by S, or C, sorry. This is S, which is I dividing by C. I we just calculate it here, so it's easy. And C here, let me show you how we calculate C. As I told you that C is the maximum or the distance between the neutral axis to the extremist fiber. So is this distance. This distance here to this point is 12 dividing by 2, which is 6. And here the thickness of this is 1 inch. Okay, so this 1 inch. So 6 plus 1 inch is going to be 7. Okay, so here we have S, which is elastic suction modulus, is equal 107 inch to power 3. And inch to power 3, because this is inch to power 4 dividing by inch, so this is going to be inch to power 3. For the yielding or the yield moment, MU, or let's say here, the yield stress is equal I know you will get confused by this. Let me make it nicer. So the yield stress is equal M sub U dividing by S. Okay, so right now how to find this? We just calculated this, which is this value, and this one should be given to us in the data. So MU is going to be F, the yield stress, times the elastic suction modulus, which is going to be 50 KSI for yield stress, times S, which is 107 inch to power 3. So this one is going to be 5,350 inch kips, or we can just divide it by 12 to get 446 foot kips. Okay, this is the unit for the moment. So right now we did calculate elastic suction modulus, and we will and the yield moment here, and we will calculate the plastic suction modulus Z and the plastic moment in the next step. Okay guys, to calculate the plastic moment, we need to, let's say, M sub P is equal Fy times Z. And Z here is the plastic suction modulus. How to calculate Z? Z is equal A dividing, or the cross-sectional area for the cross-section, dividing by 2, because this is a compression or tension area, times A. And A, as I showed you previously or earlier, so this is A, the distance between the compression here and tension forces. So how to calculate that? We need to get this distance here, which is A, or this distance will be same, because which is y hat here, or prime, because this is a symmetrical shape. So let's just take 1/2 of this cross section, okay, the shaded one here, and calculate the centroid for this one, and then we can get the A. So the centroid of this shape is supposed to be somewhere here, okay? So for the flange, the area is 1 times 8, because this was 8, the width, and this one. So, and the y here is equal to, because this one, guys, once again, different color, much easier. So this one was a 12 inch, which is 1 foot. So this one here, which is different color, is 12 dividing by 2, so this is 6 inch. Okay, and I showed you this. And this one, the centroid of this one here is 1/2. Okay, so this one here, y, is equal, which is the centroid of this, is equal, because we are taking this as a datum, 6.5, 6 plus 0.5. Okay, so this one times this one is 52. For the width, so this one for the width, different color, Okay, the whole one was a 12 and the thickness was 1/2 inch. Okay, so here this one, the area for this one is 12 for the whole one, for the whole web here, 12 times 1/2, which is 6, and this is the 1/2. Okay, 6 times dividing by 2 is 3, or we can tell this is 6 times 1/2, which is a 3-inch square, and the centroid of this one here, the centroid of this one is 3-inch from the datum point here. اعتبرنا هذا الريفرنس يا شباب. Okay, but this one gonna be also 3. So 3 times 3 is 9. The summation of A times Y is equal 61, and this dividing by the summation of area, if you remember, the centroid is equal summation of Y times area for each area. أخذناه for the flange وأخذناه for the web, dividing by summation of area. So this one is 61 dividing by 11 here. This one dividing by this, and this one is equal 5.545. طبعا هذا inch. So this is the centroid. Means here, guys. So this is the area, the centroid of this area. طبعا أكيد it does make sense إنه يكون الأعلى. So this is equal 5.545 inch. Okay. So right now, if this is equal 5.5, so the A here is equal to Y hat, which is equal, just a minute, which is equal to times 5.545. Come on. So this one is equal 11.09 inch, which is A, the distance between these two forces. So right now Z is, as we know, is equal, sorry for this, Z here, guys, is equal A dividing by 2 times A. And this is the cross-sectional area, this is a distance. They are different. A is 11 here times 2. لأنه لما حسبنا الاريا هاي كانت ايش؟ just for this shaded section. بس for the whole section راح تكون إنه هون 11 وإنه هون 11. Okay, but dividing by 2 راح ترجع 11. But let's okay. So this is a 22 inch for the whole cross section. Dividing by 2, which is this one here, times area or A, which is 11.09. This one here, guys. So this one is going to be 122 inch cube. كمان Z inch cube, but this is a plastic section modulus. Okay. So right now we can calculate the plastic moment, which is the plastic moment is equal the yield stress again times Z, and the yield stress is 50 times 122 for Z, and this one is equal 6,100 inch kip. If you divide this by 12, you will get it 508 foot kip. In SI unit, we have, let's say, Newton a meter or so on. So here this is kip foot, or we can kip inch, same thing. Okay, guys, so this, or by this, we did calculate elastic section modulus, plastic section modulus, yield stress, and or yield moment, and a plastic moment. Okay, guys, there is an example 5.2, page 196. It's the same idea. So please do it by yourself and let me know if you have any questions. And thank you so much. يعطيكم العافية.